Uniqueness of the inverse. Let's begin by recalling what we covered in the previous section. We established that a square matrix A is considered invertible if there exists another matrix B such that when we multiply A by B or B by A, the result is the identity matrix I. Now, this leads us to a very important and natural question. Is it possible for a single matrix to have more than one inverse? In other words, could there be multiple different matrices that all satisfy this condition? Before we address this, let's clarify a term we use frequently in mathematics: uniqueness. When we say a solution is unique, we simply mean that there is one and only one possible solution. There are no other alternatives. In this subsection, our primary goal is to prove exactly that if a square matrix has an inverse, that inverse must be unique. Over the next few slides, we will walk through a formal proof to demonstrate why this is the case. Theorem 3. Uniqueness of the inverse. Now that we have raised the question of whether a matrix can have more than one inverse, let us look at Theorem 3, which provides the definitive answer. The formal statement is as follows: if a square matrix A is invertible, then its inverse is unique. In other words, if an inverse exists, there is one and only one. To understand why this is true, we will use a logical approach known as proof by contradiction, which in this context acts as a direct proof of equality. The strategy we will employ is quite interesting. We will start by assuming the opposite of what we want to prove. We will assume that matrix A actually has two different inverses. However, as we move into the next few slides, we will apply the properties of matrix algebra to show that these two supposed inverses must actually be the exact same matrix. Step-by-step proof. Now, let's dive into the actual proof. To start, we will use the strategy I mentioned in the previous slide by assuming the opposite of what we want to prove. Let's look at step 1, the assumption. Suppose we have a square matrix A, and for the sake of this proof, let's assume that it has two inverses, which we will call matrix B and matrix C. Now we move to step 2, where we apply the formal definition of an inverse to these two matrices. If matrix B is an inverse of matrix A, then by definition, multiplying A by B or B by A must result in the identity matrix I. We will label this relationship as equation 1. Similarly, if we assume that matrix C is also an inverse of A, then the same rule must apply. Multiplying A by C or C by A must also result in the identity matrix I. We will refer to this as equation 2. So, we have established two equations based on the idea that both B and C act as inverses. In the next few slides, we will use these equations to determine whether B and C are truly different, or if they are actually the exact same matrix. Step-by-step proof continued. Starting with step 3, we will utilize the identity property. As you may recall, the identity matrix, denoted as capital I, acts like the number 1 in basic arithmetic. Any matrix multiplied by the identity matrix remains unchanged. To begin our derivation, let's take matrix B and rewrite it as B equals B times the identity matrix I. Now, let's proceed to step 4, which involves substitution. If we refer back to equation 2 from the previous slide, we define that because matrix C is an inverse of A, the product of A and C equals the identity matrix I. Since we know that I is equal to A times C, we can substitute the product A times C into our previous expression in place of the identity matrix. This transforms our equation into B equals B times the quantity A times C. Now that we have established our assumptions and the definitions of our two potential inverses, let's move on to the actual algebraic proof. In the next slide, we will see how to rearrange these matrices to finally prove that B and C are actually the same. Step-by-step proof continued. Starting with step 5, we apply the associative property. In matrix algebra, the associative property tells us that when we multiply three matrices, the way we group them with parentheses does not change the result. In other words, the quantity B times A, then multiplied by C, is exactly the same as b multiplied by the quantity a times c by shifting our parentheses, we can rewrite our expression as b equals the quantity b times a multiplied by c. This leads us to step 6, where we perform the final substitution and simplification. If we look back at equation 1 from our earlier steps, we know that b times a equals the identity matrix I. By substituting the identity matrix I into our expression, we get b equals the identity matrix I times c now. As we have already discussed, any matrix multiplied by the identity matrix remains unchanged. Therefore, this simplifies beautifully to b equals c. Finally, let us look at the conclusion of this proof. We began this process by assuming that the matrix A had two different inverses, which we called b and c. However, through these logical steps, we have just proven that b must actually be equal to c. This means it is impossible for a matrix to have two different inverses. We can now confidently conclude that if a matrix has an inverse, that inverse is unique. Because of this uniqueness, we no longer need to guess which inverse we are talking about, and we can use the standard notation A inverse to refer to this one and only inverse of matrix A. Now, let us move on to the final stages of our proof. In the previous slide, we established that b equals b multiplied by the quantity A times c. Real-world analogy, the unique key. Now that we have completed the formal algebraic proof, let us use a real-world analogy to help you visualize the concept of uniqueness. Think of a high-security digital lock. In this scenario, imagine that the lock itself represents matrix A. The unlocked state, the goal we are trying to achieve, is represented by the identity matrix I. The specific digital key or code required to open this lock is the inverse matrix, which we denote as A inverse. If the lock is designed perfectly, there is only \text only one specific digital code, the unique inverse, that can open it. To tie this back to the proof we just performed, if you were told that two different codes, which we can call code B and code C, both open the lock perfectly, you would eventually discover that code B and code C are actually the exact same sequence of numbers. This is exactly what we proved mathematically when we showed that b equals c. While this analogy helps us conceptualize the idea, it is important to remember that not every matrix has a key. In the next slide, we will discuss some common mistakes to avoid and the conditions required for an inverse to exist. Common mistakes to avoid. First, be careful not to assume that every square matrix has an inverse. It is a frequent mistake for beginners to forget that not all square matrices are invertible. For a matrix to have an inverse, it must be what we call non-singular, which simply means its determinant must not be 0. It is crucial to remember that the uniqueness theorem we just proved only applies if the inverse actually exists in the first place. Second, avoid confusing the matrix inverse with a numerical reciprocal. In basic algebra, you are used to the idea that the inverse of a number x is 1 over x. However, in the world of matrices, a inverse does not mean 1 divided by a. This is a vital distinction because matrix division is not a defined operation. You cannot divide by a matrix. Instead, you must multiply by its inverse to achieve the desired result. Finally, do not ignore the order of multiplication. While our previous proof demonstrated that b equals c, you must always remember that matrix multiplication is generally not commutative. In other words, a times b is typically not equal to b times a. However, the specific definition of an inverse is the exception to this rule, as it explicitly requires that both a times b and b times a must equal the identity matrix. Now that we have walked through the formal proof and the analogy of the unique key, it is important to address some common pitfalls. Let's look at the common mistakes to avoid when dealing with matrix inverses. Keeping these 3 points in mind will prevent simple errors as we move toward our final key takeaways. Key takeaways. First, let's reinforce the concept of uniqueness. As we have just demonstrated through our proof and the digital lock analogy, if a square matrix A has an inverse, it is the only one. In other words, there is no possibility of a second or third inverse existing for the same matrix. Because of this uniqueness, we can move forward with a specific notation. Since there is only one possible inverse, we can confidently use the symbol A inverse to refer to the unique inverse of matrix A rather than just an inverse. Finally, it is important to remember the logical foundation of the proof we just completed. The entire argument relied on three main pillars. 1. The definition of the inverse, which tells us that matrix A multiplied by A inverse equals the identity matrix. 2. The property of the identity matrix, which states that any matrix A multiplied by the identity matrix remains matrix A. And 3. The associative property of matrix multiplication, which allows us to shift our grouping, meaning that matrix A multiplied by the quantity B times C is equal to the quantity A times B multiplied by C. Understanding these three pillars is essential, as they are the tools we use to prove that the inverse must be unique. Now, let's wrap up this section by reviewing the key takeaways to ensure everything is clear.